Time dilation is a fundamental concept in the theory of relativity, a groundbreaking framework developed by Albert Einstein in the early 20th century. In essence, time dilation refers to the phenomenon where time appears to pass at different rates for observers in relative motion or in different gravitational fields. This concept has profound implications for our understanding of space, time, and the nature of the universe. In this essay, we will delve into the intricacies of time dilation, exploring its origins, consequences, and real-world applications. The concept of time dilation stems from two distinct yet interrelated aspects of the theory of relativity: special relativity and general relativity. Let us begin with special relativity, which was formulated by Einstein in 1905. Special relativity primarily deals with the behavior of objects moving at constant velocities, particularly those moving at a significant fraction of the speed of light. One of its foundational principles is the constancy of the speed of light in a vacuum, denoted as c. No matter how fast an observer is moving relative to a source of light, they will always measure the speed of light as c. To grasp the concept of time dilation and special relativity, consider the famous thought experiment involving two observers, one stationary on Earth and another traveling in a high-speed spacecraft. According to the theory of special relativity, as observer B accelerates to a substantial fraction of the speed of light, their perception of time begins to change. From the perspective of observer A, time for observer B appears to slow down. In other words, the clocks on the spacecraft run slower relative to the clocks on Earth. This effect becomes more pronounced as the relative velocity between the two observers increases. It's important to note that both observers would consider their own time to be passing normally. This principle is encapsulated in the famous equation. Here, delta t represents the dilated time experienced by observer B, delta t is the proper time experienced by observer A, v is the relative velocity between them, and c is the speed of light. The consequences of time dilation and special relativity are not merely theoretical. They have been experimentally confirmed many times, most notably through particle accelerators, which accelerate subatomic particles to nearly the speed of light. These experiments consistently yield results in accordance with Einstein's predictions. Moving beyond the realm of special relativity, we arrive at the broader theory of general relativity, formulated by Einstein in 1915. General relativity extends the principles of special relativity to include gravity, treating it as a curvature of spacetime caused by massive objects. In this context, time dilation arises from gravitational effects. According to general relativity, the closer an object is to a massive body, the slower time appears to pass for it compared to an observer at a greater distance. This is known as gravitational time dilation. It's a consequence of the way spacetime is curved by mass, causing the paths of objects to deviate from what we would expect in flat space. A classic example of gravitational time dilation is the phenomenon observed with Global Positioning System satellites. These satellites orbit the Earth at high speeds and are subject to weaker gravity than we experience on the planet's surface. As a result, the clocks on board these satellites run slightly faster than clocks on Earth. To ensure accurate GPS navigation, the satellite's clocks are adjusted to account for this relativistic effect. The mathematical expression for gravitational time dilation is given by here, delta t is the dilated time, delta t is the proper time, g is the gravitational constant, m is the mass of the massive body, r is the distance from the center of the massive body, and c is the speed of light. This effect demonstrates that the closer an object is to a massive body, the more significant the time dilation.